So, in our subject selected topics in decision modeling, we are now in our 36th lecture, that is simulated annealing. Simulated annealing, as you can see, it is a random search method developed by Kirkpatrick and others in 1983 based on the physical annealing process, and highly compared to hill climbing. Only thing, it also allows downward steps or transitions to weaker solutions and through a series of random moves. Now, how it happens? Look here, in this case you see a function has got multiple peaks and troughs. So, we have a global maximum, there could be a local maximum also. If you start the search from a random point A, obviously you move up the global maximum, that is the usual hill climbing method, where with every iteration we try to go to a higher value and discard any value that goes lower. And but then in a hill climbing method, typical hill climbing method, if you start from random point B, then through hill climbing you do not lead to the global maximum, you lead to a local maximum, right. That is a peak point definitely, but not the best possible peak. But assume, supposing at random point B, if you are allowed a downward movement and if you go let us say to a point say here, right. So, what is possible, then you can do hill climbing and you can reach to the global maximum. So, this is essentially done by simulated annealing. What is done? First at high temperature is assumed. So, as if you reach, you raise the entire thing to a very high temperature T, which is a very high temperature. Now, at a high temperature, a function is used which is called the metropolis function. Metropolis function. This metropolis function is such that it actually has got a very high probability to accept a point which is downhill. So, the point is, look here, suppose in an iteration it is a minimization problem, So, in a minimization problem we have a function value f x 1. In the subsequent iteration we got a new point x 2 from x 1 and I got a point x 2, the value is f x 2. So, see what has happened, in before iteration I had x 1 function value f x 1, after iteration I got x 2 function value f x 2. Problem is minimization, right. So, if f x 2 is lower, there is no problem, everything is fine, it is a minimization, we are moving towards the global minimum, is it not? See, we are moving global or local, we do not know, we are really moving lower, there is no problem. So, there is no need to really look at the metropolis function or conditions, you simply accept that point x 2. So, this is how the method goes. But on the other hand, suppose f x 2 is actually higher. See what has happened. We started with x 1, we got another point x 2 which is higher, and the problem is minimization. So, what has happened? We wanted to go towards a minimized points, but here as if in a figurative sense we are going downhill. Here the top of the hill is minimum point and bottom of the hill is those points which are not very rather high values. So, in that sense what happens, then we have to apply metropolis condition with a high probability of accepting the current f x 2 or the point x 2, even though it has got a higher value, right, of the function of the function. So, this is the essential idea that in a figurative sense, for a maximization point, if it is going up then no metropolis condition, if it is going down then metropolis condition. So, however, if it is other way round, so let us say the minimization function. So, this is a minimization function. So, you see this is a local minima, this is a global minima. So, this side is x, this side is f x. So, this is the global minima. So, let us say we are here, say we are here, we are going down. So, this point is fine, but we are going up. So, is it to be taken that up point is taken or not? See, the up point could be while in the search for global minima, or the up point could be somewhere here and then we are going up. So, if we are here and we are going up, it is good, because we are avoiding the local, this is local minima, this is global, right. So, if we are at starting from here, so this is x 1 and this is x 2. So, we are going up, this is good, we are going towards global max minima, but if it is here and we are going up, that is not good. So, therefore, going up has got both good and bad situations. So, what really it does, if you are at a high temperature, so initially when things are at a very high temperature, at that time chances of going downhill is actually favored. The probability of accepting the value if you are going downwards in case of maximization and upwards, I mean the function value is higher, in minimization we can still accept, but slowly, very slowly we reduce the temperature, and as the temperature goes up, the probability of accepting the reverse direction movement reduces, is not, that is the annealing. That is where the comparison with the physical annealing process comes in. So, same thing is written here, inspired by annealing process in which materials are raised to high energy levels for melting and are then cooled to solid state. The probability of moving to a higher energy state instead of lower is the metropolis function P equal to e to the power minus del E by k T, where k is the Boltzmann constant and del E is the positive change in energy level, T is the temperature and k is the constant. So, for our purpose we shall take k equal to 1, although everyone knows in typical physical processes the k is definitely not 1, but ours is not really truly annealing process, we are just drawing an analogy. So, we take k equal to 1. Temperature is high at the beginning. So, when we start at a very high temperature, at that time these probabilities are high, right. As temperature goes down, probability for moving to a higher energy state instead of lower will be less and less. So, as temperature is lowered, probability of a downhill move gets smaller and smaller. So, here what is uphill, what is downhill? Uphill is global maxima or global minima, downhill is opposite direction. So, if temperature is lowered very slowly, the best energy state is resulted. So, as you keep lowering the temperature, the process finally comes to a steady state and the best energy state is resulted. So, this is the physical annealing process. The objective is to line up all the atoms on crystal lattice sites without any defects. This is the lowest energy state for this set of atoms, is all right. So, you see they are very nicely arranged. So, when the temperature is hot, then all those things, and when temperature is cool, it is a low energy state and it is much more stable. So, anneal the material to reach lowest energy state, first raised to very high temperature, allowing the atoms to move around and then cool very slowly. It restricts the range of motion till the atoms freeze to lowest energy configuration. So, that is the physical annealing process. Now, in the assay or simulated annealing algorithm, what exactly we do? Let us see that. Randomly generate a solution string, evaluate the fitness function for all the solution string, then set initial and final temperature, iteration, how many iterations at each temperature. So, while final temperature equal to initial temperature, for fixed number of iterations, randomly introduce a perturbation, right, a small change to the current solution string. So, that means from the point that you start, choose a point nearby. So, evaluate newly generated string, always accept the new alternative if it reduces the cost. So, this algorithm is given for minimization. This is given for minimization of cost. This the example also that we shall take for minimization. So, always accept if the new alternative reduces the cost, because it is a minimization. So, always accept, right. So, that means from x1 to x2, fx1 to fx2, if fx2 is lower, always accept, right. But randomly accept some alternative that increases the cost. What happens if the reverse, that means fx2 is greater than fx1, then apply Metropolis criteria. All right, this is what it is. So, after a certain number of iterations, then you again change the temperature. So, this is the essential process of the simulated annealing algorithm, right. So, now look how what is the analogy, the physical analogy, that we have the metal versus optimization problem, energy state versus cost function, temperature versus control parameter, crystalline structure, the optimum solution. So, global optima global optima solution can be achieved as long as the cooling process is slow enough, that means very slow. So, why it should be very slow? The point is at in the initially we should be able to evaluate many points, right, and then from those many points we shall see what is that particular point which is showing a very good what you call response, so that the system can actually go to the global minima or global maxima. But please remember, like in GA, the global optima is not guaranteed. So, it is not an exact method, it is an inexact method. Like all inexact method, the optimum point is not guaranteed, right. So, this is a shortcoming of all such evolutionary algorithm techniques, right, or meta heuristics, which is a general characteristics that I have told you before also, right. Now, what are the steps? So, here are the steps once again: input the initial solution and the initial temperature, generate and estimate the new solution, accept, then update solution, adjust temperature. Now, the update solution is done for a number of iterations obviously, and only then you adjust temperature, right. And if you cannot accept, then adjust temperature, and then terminate, no, and then go back. So, like this, that is the steps of the simulated annealing. Let us see the algorithm. So, this is the algorithm that we shall follow for in the example. So, choose an initial point x0, a termination criteria epsilon, set temperature T to a sufficiently high value and number of iterations n to be performed at a particular temperature, right. So, take a temperature value, decide on how many iterations to be done at that particular temperature, get an initial value and a termination criteria. Now, calculate a neighboring point x t plus 1, which is an n x t, means n is a random thing. So, randomly. So, then in other words, choose a random point around x t, right, that call it x t plus 1. Now, see, this is again for the steps are for minimization. So, that must be remembered. All these steps are for minimization problem. For maximization problem, the directions should be opposite, right. So, the question is that the net change of energy should be negative, because here energy is nothing but the functional value, right, that is del E is nothing but del F, change in functional value. So, if the functional value change is negative, then accept it, right, without any question, and set t equal to t plus 1, that means go for the next iteration. Otherwise, create a random number r in this way, that is r from 0 to 1, and this is the Metropolis criteria. So, take this is the probability value, the e to the power minus of del E by t, k equal to 1, already I have said. So, basically original function, right. So, that was the function e to the power minus del E by k t, where k equal to 1. So, that is that function, Metropolis function. So, if r, that probability that you have taken the random number, if the random number is lower than this, now mind you that as the temperature is reducing, this number will reduce also, is all right. So, what happens at high temperature, this value is high, at low temperature this value is low. So, chances of acceptance will be high when T is high, is all right. So, therefore, there will be high chance that, assume the R is 0.5, 0.6, around that, obviously it will be accepted. So, if so, then accept it, then set t equal to t plus 1, else go to step 2, means discard this point and generate another point, is all right. So, if this is accepted, point is accepted, if it is not accepted, point is discarded. Then in the step 4, check whether the new x is very near to the old x, right. That means, no more hill climbing is possible, because if you have reached the peak, any nearing point will not be good enough, right. So, t will be small, so terminate. Else if if T mod n equal to 0, then lower T according to a coding schedule go to step 2. That means T mod n means that number of iterations have been done, right. So, in that case lower the temperature and again generate a new point. So, that is the essential steps of simulated annealing. So, having understood that, let us see an example. So, this is the example, find the minimum value of a function using simulated annealing, minimize f x equal to 500 minus 20 x 1 minus 26 x 2 minus 4 x 1 x 2 plus 4 x 1 square plus 3 x 2 square along with some x 1 x 2 conditions, and assume temperature reduction factor C equal to 0.8 and maximum number of iterations as n equal to 2. Having said that, I have taken these ratios of 0.8 and only 2 iterations because of we are doing it in the class. When you do computer iterations, you should take more iterations, not just 2, maybe 10, 20 iterations, so that you explore the solution space sufficiently for every temperature. Is it all right? So, those values, and probably depending on the problem, you may reduce the temperature more slowly instead of 20% in each step. Is it all right? So, that is how things go. So, how to generate the temperature? So, the first task is to calculate the initial temperature T. So, usually what is done, we take some random points. So, in this case we have taken 4 random points. So, for in these 4 random points, that is 2 0, 5 10, 8 5 and 10 10, we have calculate the function value. Recall that was our original problem, minimize f x. So, we find the functional value in each of those random points. For example, in the first point 2 0, the value is 500 minus 20 into 2, 26 into 0, 4 into 2 into 0, 4 into 2 square plus 3 into 0 square equal to 476. So, that is the functional value at point 1. Similarly, we can find functional values at point 2, point 3 and point 4. So, when we have found out all these functional values, so if I take the average of these functional values 476 plus 340 plus 381 plus 340 by 4 equal to 384.25. So, what is this 384.25? This is our initial temperature. So, the temperature is nothing but a functional value, right. It is a functional value. This functional value is you might think that that is the kind of, this is the kind of functional value randomly it's we are around this point, right. Now, we have to choose an initial design point randomly. So, again through a randomization process we got the initial point, let us call it 4 5. So, 4 5 is our initial design point. So, we have computed the initial temperature T by taking 4 random points, and we have taken an initial design point x 1 which is 4 5. Is all right. So, that is the first. Then after that we go to the next step. So, at the next step we find the functional value at our initial design point 4 5. So, 4 5 is our initial design point, the function value is 349, right, and this is our first iteration. So, what we do, generate the new design point in the vicinity of the current design point. So, this is our 349 is our current design point. So, select 2 uniformly distributed random numbers u1 and u2, right. So, 2 random numbers we have to obtain, assuming those 2 random numbers are 0.31 and 0.57. Why are they 0.31 and 0.57? They could be any other number, right. Nothing very great about 0.31 and 0.57. It is a random number we have obtained from calculator or by some other method. So, these are the two random numbers. Assuming plus minus 6 accuracy, so since x1 is 4, so actually x1 point x1 is small x1 and x2. So, these are the two variable. So, which gives x1 equal to 4 and x2 equal to 5. So, this is the, that is we are calling point x1, the capital X1, right. So, now x1 you will be varying because of plus minus 6, minus 2 to 10 and x2 minus 1 to 11, 4, 5. So, like this. So, using that random number, so what will be the new value? New value will be minus 2 plus u1 into 10 minus minus 2 and minus 1 plus u2 into 11 of minus this 2. So, this point comes to 1.72 and 5.84. So, this is going to be our new design point. Now, look here, in the new design point, what is the function value? So, if we put it in f(x), this point 1.72 and 5.84, what do we get? We get 387.7312. Now, how good is this point? This is good or bad? Tell me. The original function was one of minimization, right. When x1 is equal to 4, 5, that means capital X1, the initial point, then the function was 349. Now, after iteration, we got a new point 1.72 and 5.84 and the function value is 387. So, it is a good or bad? In a traditional hill climbing sense, this is a bad point. Why? Because it is a minimization problem and in the new design point, the function value is increasing. But we have seen that to really cut off the global minima from our consideration, we might also sometimes accept lowering of value or in this case increase of value going in the opposite direction based on the metropolis criteria. Let us see what is that. So, the del f in this case is f2 minus f1, that is 38.7312, that is our del f. So, what we have to do? We have to apply the metropolis criteria. So, let us take a random number, assume that that random number is 0.83. So, this is our random number 0.83. Now, we have Px2 is e to the power minus del f by kt and k equal to 1. So, we see this value is 0.9041, right. So, what we got? We got r is less than Px2. So, our random number is less than, that means we accept this point. So, although the point is a bad point, but we still accept this point as the objective function value f2, although it is higher, but still accepted, and usually this has happened because of high current temperature. That is how this probability has come such a high value. Got the point? So, that is how it is done, and further if we do iteration at the second iteration, again by the same method we take two random numbers and with a plus minus 6 accuracy around this point, that means between minus 4.28 and 7.72, and these two ranges, again we take using these two random numbers a new point, and this new point is x3, which is 6.76 and 8.6. So, when we put that, the new function value comes to 313. Look here, the old function value was 387. So, from 387 we have actually come down by 74. So, this is a good thing, it is a minimization problem and we are going down. So, that means the point should be accepted. There is no need to apply metropolis criteria. Is it all right? So, that is the thing. So, we we have done our 2 iterations, Metropolis criteria not required. Since a cycle of iteration with the current value of temperature is completed, now we reduce the temperature to a new value. Actually it will not be 0.5, this will be 0.8, right. So, whatever is the value 300 something, that will be coming, right. So, that will be our new temperature, and in the step 3 generate a new design point, and like this we continue, is all right. So, like this we do the simulated annealing process, right. And let us see further some drawbacks of simulated annealing. Although can avoid formation of any cycle, the rate of improvement is very low. That is the good bad point. Assay does not have any memory to keep records of previously visited solution. So, the point is we might come back to the same solution again, right. So, this is the simulated annealing method. We shall see more such methods in our subsequent lectures, right. So, thank you very much.